Thanks, Allison. I'm Mark Bullock at the Science and Technology Corporation. My talk is about SO2 in the lower atmosphere. I've been kicking these ideas around with David Grinspoon at PSI, and I thought this would be a good topic. It turns out that SO2 has been a common theme in this conference. It connects both with the difficult to explain abundance profiles in and above the clouds, as well as its variability, and of course its probably major role in interactions with the surface. So I just thought we'd point out a few things about SO2 in the lower atmosphere things that we know and things that we don't know. So SO2 is a precursor, of course, of the clouds. Those two reactions, the oxidation of SO2 and then the formation of sulfuric acid, are what are photochemically produce liquid sulfuric acid water droplets. The modeling work that David and I did in 2001 showed, with a sort of a simple cloud model, showed that you need at least about a part per million SO2 to get cloud formation of sulfuric acid. Otherwise, as we go through our evolution models, we find that water clouds appear instead, even at fairly low water vapor abundances. And clouds the sulfur is interesting because clouds are responsible for climate change via competing effects. The high albedo, of course, of the clouds, the fact that the clouds themselves are a greenhouse effect, a strong greenhouse effect, and contribute about 125 Kelvin to the surface temperature. And SO2 is also a minor greenhouse gas. I noticed on someone's talk about, it was about ice shell data, the 2.46 micron absorption bands you can see from Earth, and that's right in the middle between major CO2 bands. So it does have an absorption effect and a greenhouse effect. So the net radiative effects of SO2 on surface temperature are fairly complex. We're sort of interested in what the role of SO2 has been over long periods of time, not necessarily just the present. So here's the conflicting data that I don't know if anyone's mentioned so far. The plot on the left is just sort of a general view of the different gaseous species, and you'll see that SO2 on the left is typically from the Pioneer Venus mass spectroscopy data about 180 parts per million below the clouds, and pretty much assumed to be a straight line, well mixed to the surface. But on the other hand, the Soviet Vega probes with their Vega probes, both 1 and 2, showed a dramatic decrease of SO2 towards the surface. And this was using a very different technique, an in situ UV spectrometer that measured the SO2 abundance in a cell. And what they found, both for Vega 1 and Vega 2, is a monotonic decreasing SO2 abundance to something much lower near the surface. And now, obviously, the implications are very large because there's just almost all of the mass of the SO2 is in the lowest scale height. And so if the lowest scale height is really only 10 or 20 parts per million, the global abundance of SO2 is quite a lot less on the right-hand side. And this was in a paper by Berthaud et al. In '96, and I know Thomas Wiedemann is on, and if you have any comments, Thomas, about this, I would love to talk to you about it, because this is not something that we've been widely discussing, and it's quite a remarkable result. So the implications are that at 180 parts per million, I calculate this is column density of about 18 grams per square centimeter. For the Vega result, we get a column density about 1/10 of that. And there's a big difference, and there's some important implications of that difference. Just for comparison, the Venus cloud's column density is about 35 milligrams per square centimeter. That is the aerosol mass. And the Earth's SO2 column density is about a milligram per square centimeter. So the sulfur chemistry in Venus is obviously much more important than it is on Earth. And of course, we've got these wonderful efforts of laboratory efforts of reactions, and a lot of it has focused on SO2 reactions with surface minerals, and particularly calcite. The little picture on the upper right is from a Fegley and Prin 1989 paper that really first did these the kinetics of these reactions, the reaction I show there. So the thermochemical equilibrium of this reaction, of that reaction, it results in about 2 parts per million SO2 at the surface. So this implies that if the Pioneer Venus results are correct, the atmosphere is wildly out of equilibrium with the surface. What Fegley and Prin calculated was it would take about 2 million years for the surface to take up all of the SO2 in the atmosphere if you just had free calcite reaction surfaces. And that this implied a volcanic flux of about 1 cubic kilometer per year, which I'll come back to later because it's an important constraint on what the current volcanic flux is today. And there are several lines of evidence that converge on a number close to this by a factor of 2 or 3. So these very many laboratory experiments we're hearing about, and I couldn't really sort of condense everything into what has been talked about already, but clearly, Filiberto showed that the exact mineral composition greatly affects the reaction rates. Although anhydride is usually the Allison also is usually the product of these experiments. I even note that Filiberto showed that whether the basalt is tholeiitic or alkaline has a big effect. So there are for whatever reactions that occur with SO2. So as Marty Gilmore said, the type of the lithology that you have is an important factor in how the surface reacts with the atmospheric gases. So if this gradient is real, the one from the Vega, you could sort of interpret this gradient to mean a flux into the surface, and that's an extreme sort of assumption. Because normally you would think of the gradient as a result of gas-gas reactions. But if that flux were, if that gradient really implied a flux, this is about 40,000 times faster than the Fegley and Prin results, and probably similar reaction rates that the more modern experiments will show. And then Alan yesterday pointed out, or maybe Monday, pointed out that the calcium to sulfur from Venera XRF is not really consistent with the formation of large amounts of calcite. So we have these conflicting pieces of evidence from the laboratory. It looks like SO2 reacts vigorously with surface minerals, but XRF data from the surface of Venus doesn't really support the very widespread thick layers of calcite, of anhydride. So, and just to talk about the current volcanism issue, for our Venus climate evolution models, we've assumed about 3,000 parts per million SO2, which is roughly the saturation of SO2 in basaltic magmas. However, I would point out that there are much more sulfur-rich eruptions on the Earth, like Pinatubo, which result from the magma ascending through sulfate layers. So they're super enriched in sulfur. And Pinatubo was famous because it injected sulfates into the stratosphere, forming basically a Venus cloud layer, a very, very thin one called the Jung layer in the stratosphere. So it's very much a Venus-like process that happens on Earth once in a while at a very, very small scale. And when we account for the diffusion of SO2 into the surface, as well as the kinetics from the experiments, David and I figured in our 2001 paper that if volcanism were to cease, the clouds would disappear in about 30 million years. This is in contrast to the 2 million year number that Fegley and Prin cited, but we considered the diffusion of SO2 into the surface to fresh reaction surfaces. And of course, active volcanism produces fresh reaction surfaces. And the volcanic rate to explain the steady state existence of Venus's clouds requires about half a cubic kilometer per year. I think this is really interesting in light of Jim Head's very interesting talk. In fact, it's one of the things I think that motivated our work on this, whether SO2 is sort of a fossil result or whether it's really actively needed to be injected into the atmosphere to really explain the clouds. I mean, of course, we don't know if the clouds have always been there. Venus might have been cloudless 1,000 years ago or 2,000 years ago, maybe, and we wouldn't know. So some notes on the physical weathering. The soil mechanics experiments on the Venera lander show that the basaltic surface of Venus is much weaker than on Earth, which leads to the possibility that the surface is very porous and therefore a good physical sink for SO2. And the friable surface suggests that the weathering products like sulfates may be removed and transported by surface winds. So we can sort of imagine the same way we think about how dust is lifted from the surface of Mars and preferentially deposited in certain areas, and whether there's something like that going on Venus, where the sulfate rinds are preferentially stripped and deposited in other locations, for example, where there are dune fields. Just an idea that might help explain why the Venera results were not that high in sulfur, but the laboratory results and sort of the theory suggests that sulfates should actually be quite abundant on the surface. So in the meantime, I'd like to talk about this catastrophic versus equilibrium resurfacing, which was a concept developed in the early 90s after, with the first Magellan results. And I wanted to emphasize that these are end-member models, and basically to describe the crater distributions, the fact that they're randomly distributed and that only a small percentage of them are impacted by volcanism or tectonism, although the crater floor filling stuff of Herrick et al. Is, changes that view. But in 93, Bullock, Grinspoon, and Head wrote this paper with a Monte Carlo model that tried to explain the simultaneous existence of randomly placed craters and just a small number of embayed craters. And we found that about 2 cubic kilometers per year would explain the cratering record that we see today. So so catastrophic resurfacing, whatever mechanism, whatever crazy mechanism might have done that, is not inconsistent with current volcanism today. That's what this paper basically says. That we may actually have a volcanism rate that's fairly similar to the interplate volcanism rate on Earth currently. Good. Okay, so I'll skip the surface emissivity because people have been skirting around this. This is the famous result from Smrikar et al. 2010 showing lower emissivities at the top of the Imder volcano, and it could be that we've got active sulfate formation on the older, which we see on the older plains, but not at more regional, not at the top of volcanoes where there's recent volcanism. Is that all I had? I guess that's it. Okay, thanks.